My name's Robert. I'm a data scientist at Datatonic. I came from Edinburgh. I did a degree there in AI and mathematics. Datatonic, we're like a small consulting company delivering bespoke machine learning solutions. So yeah, we're kind of a team of different experts. And this project was one of our kind of fun projects that we did for, just like demo purposes. It all started with a hackathon organized by TfL, which they kind of gave us the data that we used, and we took part in that. Of course, you can probably tell that the motivation is quite obvious. You want to avoid congestion in London, and we tried to predict it so that you can avoid it. The main motivation is to kind of avoid gridlocks, because as you can imagine that every big city struggles with bad traffic, especially in the peak hours. However, the massive cities struggle from another problem. It's like a whole other level where so many cars are in the city center that it's also hard to exit and they can't leave, which makes the problem even harder. And if you could prevent it, if you could see it happening from half an hour before that, and for example tune the semaphore lights to not allow that many cars in, you would be able to basically avoid the situation completely. Now we built like a whole delivery system for this type of data that would work in kind of like a live scenario as well. We only had kind of like a batch mode where we streamed new fake data in the system to prove that it works, but kind of we only worked with 3 months of data. You can see that there is some kind of ingest component in the beginning, collecting the sensor data. Then we need to do some data processing. We need to do some inference on the machine learning system. And once we have that inference, we kind of deliver it to two spaces. We deliver it to PubSub, which is another messaging system, which delivers those predictions to either a visualization tool or an API that can be used by the traffic controllers. But it also stores it in like some kind of a data warehousing solution so that you can then kind of come back to it later and do some more data analysis on it, for example, with some visualization tools. Now, we use two main kind of frameworks to do this. And of course, as any kind of machine learning problem, we had two main issues. The first one was pre-processing all the data, and the second was the machine learning bit. So for pre-processing, we use Apache Beam. We're big fans of it. We use it for Orca and all ETL in-house, and then TensorFlow to define the neural networks to do the inference. I'll go quickly through the Beam stuff as well, because I think it's really interesting and it's probably relevant for anyone who actually wants to do machine learning, because as you'll find out, if you want to deliver a system in a week or two, you'll spend most of the time in the pre-processing stage. Now, the idea behind Beam is that you split the code definition of the pre-processing pipeline from the place where you run it. So you have two kind of ways to define the pipeline. It's either in Java or in Python. Those are the frameworks or SDKs right now. Of course, there could be more in the future. But that is actually decoupled from where you run it. Usually when you run large ETL jobs, you want to run them on multiple workers. So you want to run them on some clusters. A popular one is Apache Spark, but then we work a lot with the Google Cloud Platform, so we used to use the Dataflow runner the most. But of course, some other ones like Flink and Apex are kind of coming in as well. Oh, right, and an important thing is that it can do both streaming data and batch data. So while your classic Hadoop or MapReduce can only work with batch, the same pipeline will actually work for streaming data as well, which is really neat. But only the one defining Java right now. So, who can tell me what this piece of code does? Any ideas? It's like Yeah, exactly. So this is like the hello world of all ETL tools. Just give it like a large piece of text and it will count the words. You can see that the syntax is slightly not very Pythonic. There is a lot of pipeline operators and like something that looks like bitwise shifts, but those operators are actually overridden. So this is really just a way to define the pipeline so that it looks neat. You can define the functions yourself. You can either use some inline lambda tools or you can just define them in a separate function. It's actually quite neat to work with this. And then you can test the code locally, whether it just works, or you can just then launch it on some kind of a cluster manager where it will scale to 100 workers and with the same code, which is really nice. So our problem with congestion was basically getting from the raw data into something that we could work with in a machine learning system. Now, the raw data looked really ugly. There was a lot of kind of like metadata around it, but basically what the data was. At intersections, there are all these magnetic loops which control whether there's a car above them or not. And they are today mostly used to see whether there are cars passing through the intersection, and they kind of control the lights in an immediate way. There are 15,000 of these sensors around London, and they kind of poll whether there is a car above them 4 times per second. So if you think about this, the scale of the data is 60,000 data points per second, and this only grows, right? So imagine you have days, you have months of data. It grows very quickly. So in the hackathon, we got 3 months of the data, and you can already see that it was quite a lot. It was 5 terabytes, it was 120 billion lines, and you actually need to have a lot of compute power to just process that. Yeah. So basically what we did is like each line here corresponds to some, I think like 4 bits. So it's like that 1 second. It has a few sensors in it, but we decoupled those two. Basically our output was, we did aggregations by 5 minutes so that those windows is actually something where you can see something. And we grouped them by sensors. So basically we then outputted it to BigQuery, but like, yeah, this is what our rows looked like. Basically 5 minutes worth of zeros and ones to process it further to do some stuff with actually some, that would give us some information. Right, so this is what our pipeline looked like in Dataflow. It was really just kind of like, yeah, reshaping it from the original size, and then we're doing it under 5 minutes, but it was already quite a beast of a job. Like we were, I think, running hundreds of workers, and it took hours to complete. Some of them we did overnight. And, like imagine that like you do something and then you say like, oh yeah, well, but actually, I actually wanted a different traffic metric. So we need to run the whole pipeline again. And, like that adds up. Yeah. Now, this is actually a video, maybe I can show it to you. So when we had the pre-processing, we thought, oh yeah, that's neat. Before we do any machine learning stuff on it, let's try to visualize it. So this is in processing, and it's just like a visualization where you display all the sensors on map, and kind of the white dot means there is a car passing over the sensor, and the blue dot means there is no car over the sensor. This visualization actually also worked in real time. If you hooked a PubSub upstream, this would work real time. So it was quite neat. Okay, let's go to the next slide. Cool. So just to introduce you before we get into TensorFlow stuff, what is actually that we computed and what is it that we were trying to predict? Because what is congestion? You need to think about it a little bit before you can derive it just from thinking whether there is a car above the sensor or not. Because imagine that there was no car over the sensor for the past 5 minutes. Does it mean that there was no car passing over the 5 minutes? Or does it actually mean that there were 2 cars standing there for 5 minutes, not moving at all, and there was a gap in between? Where there was no car, right? So just from the occupancy, which is how much time of those 5 minutes the sensor is occupied, and flow, which is counting how many streams of ones that are continuous are in those 5 minutes, we need to come up with some metric that is representative on how congested the road is. We did a little bit of domain research where we tried to figure out how to derive speed, so there is some kind of a theory on it. Speed is flow/density, and then we looked at on each road or each intersection, which is how we kind of divided the sensors per intersections. We had a look at basically the max speed that the cars were attaining there from the data. So let's say this was, I don't know, 40 miles per hour. And then we looked at the relative speed, so the one that was there at the moment. And that was kind of our relative congestion metric, where we thought like, okay, you know, if that is 0, that like the relative speed is 0 and the maximum speed is something, the road is congested. If the speed matches the max speed, the road is completely free. We did again some more visualizations in Tableau, which kind of show you the west corridor leading into London, where basically the red ones, the red intersections correspond to the congested ones, the green ones to where the traffic flows nicely. Now, what we were trying to predict was basically this congestion measure. Now, finally into the machine learning stuff, once we had the data defined, we decided to use TensorFlow as the library. You know, I mean, you're probably all familiar with it quite well. It's very popular. Right now, it's actually, like, it's getting a lot of traction, right? And like recently, a few months ago, there was the new version 1.0, which introduced quite a lot of new stuff. I actually encourage you, that is actually the link inside. It links to the Dev Summit from TensorFlow. It shows quite a lot of videos where the engineers from the TensorFlow team are introducing the new features. Some of our favorites were the high-level APIs, which are basically the layers and the estimators, which take away all the boilerplate code that you needed to write in the past, and now you can just do stuff more like in the scikit-learn type, where you define an estimator and you do .fit and point it towards your training data, which is much neater. And like when you copy someone else's code that you found somewhere on GitHub, you can actually plug it into yours straight away, rather than in like before, everyone had their own model class, which you had to, you know, kind of disassemble, and just only took to take the relevant bits. It also introduced some of the other non-neural network classifiers as well, such as random forest, some SVMs, some clustering, and Gaussian mixture modeling. They are starting to do the XLA stuff, the faster linear algebra, but it's, I mean, it's still in infancy, right? It doesn't work very well yet, but they welcome contributions a lot. Right, so for our problem, we used RNNs. Are you guys familiar with RNNs? Have anyone worked with them? Awesome. So I'll try to go over the concepts a little bit as well, but I mean, you probably know already. So we used this to model our time series, and we did it as a regression problem. So based on the past 40 minutes of data, so if you think about it, it's 8 timestamps back, because we had 5-minute intervals aggregated together. We tried to predict a value that was 40 minutes ahead. Basically, looking at the past 40 minutes, try to predict whether this road is going to get congested. Now, why that should be possible? You can say like, yeah, well, but traffic is random, or like, yeah, but traffic is just, you know, like, yeah, it's going to be congested, you know, when people go to work, and it's going to be congested when people leave work, and, you know, at midnight, it's not going to be congested at all. Like, how difficult is that, you know? I mean, but the thing is that we're trying to look for different patterns. We're trying to look for the ripple patterns that show when, basically, you know, if your cars are slowing down somewhere, or like you can also see it, yeah, anywhere in the traffic if you're just riding, right? That, you know, like if someone suddenly brakes, all the cars brake behind him, and that wave actually ripples all the way back. And when we're modeling the corridors that lead into London, that is actually something we're trying to capture, that if there is a congestion somewhere in the center of London, that is, we know that like, okay, this is going to spread all the way back. And that was the complexity we were trying to capture. Now, RNNs showed a very good kind of like results in the NLP kind of area, but and that was neat. But then we also saw a few papers trying to model time series with them, and you saw like, yeah, well, let's try this, and the approach actually works quite well. So to give some introduction into how RNNs work, it's basically, if you look at that image with the loop, that's kind of the basic one. So we have some input, which is the current state, which would be the current state of traffic at this instant, or in this 5-minute window. And then out of that, you get some hidden state. That's, again, just like another layer. It's like a matrix multiplication. And out of that, you get your output state, which is kind of like the output layer. However, when you move on to the next one, you don't only look at the hidden state that you got from the current timestamp, you also look at the previous one, right? So whenever you're at time t, which is the one in the middle here, you look at what was inputted in this time step, but you also look at the hidden step from the previous one. And what you do some simple equations. The f there actually stands for hyperbolic tangent. You multiply a matrix with the current state, you multiply a matrix, which are your weights, with the previous hidden state. You take a hyperbolic tangent, and that is your hidden state in this time moment. Then you multiply it again with another matrix, apply softmax on it. That is your output now. It's quite simple, right? The forward pass is always simple. However, it's when you go back when you get problems, right? Because you have dependencies. So when you do the backpropagation, which is in RNNs called backpropagation through time, it sometimes causes issues, especially because the previous state depends on the current state depends on the previous one, and that one on the one before, the one on the one before, and it chains basically all the way to time 0. However, both of those functions that we are using are sigmoid and hyperbolic tangent. They get saturated at the ends, right? So towards 1 and towards 0, the gradients are very close. They're very close to 0. So basically, it is very similar to training a very deep neural network, which only has sigmoid activation functions. Your gradients are going to vanish. They're not going to explode, mostly because you can just clip them, but the vanishing gradients are a real issue because they need to backpropagate kind of through time, but I mean, you can also just say like, okay, I only want to go 5 time steps back or something. Those matrices actually that I showed you, so the U, W, and V, they are shared, right? So you do an update, and like if you were to expand the chain rule, it would go all the way back to the first hidden state. But I mean, you can just clip it, and you say like, okay, no, this is my update on those matrices, and in this step, I'm going to update them like this. Anyway, the RNNs, they still have this issue that like those gradients vanish. Now, there are some smart people who, thought like, okay, well, let's solve this, and it was actually quite a while back. I think in the 90s, when they saw like, yeah, well, there are these long-term dependencies problems. Let's try to use LSTMs so that we can also get some values from those inputs far back. Now, again, this was motivated or like kind of like made popular mostly in the NLP field, where if you try to model your sentence, which was slightly longer, and you start the sentence with something, then you do like a middle sentence which describes that, but then you try to go back with the verb that references the first word of the sentence. If there's 10 words in between, you completely lost track, but you need to actually capture its complexity. And LSTMs are a step forward that help you do that and actually help you model the long-term dependencies. Now, yeah, how do you do that? That's basically, it's quite similar, right? It's just a little bit more complicated equations. But if you think about it, it's again just getting some input in the current timestamp, getting some hidden state from the previous timestamp, and then computing the current hidden state, and then getting some output. However, you do like a little bit more of linear algebra. You have some gates, you have some input gates, you have some forget gates, some output gates, which are again just like sigmoid functions of, they have their own weights. So basically the input gate is something that is trying to regulate. So notice it's a sigmoid function, so it's a vector that gets squashed to zeros and ones. It is something that is going to try to regulate how much of the current input I'm going to use in the current state. So it is going to try to find some equilibrium between looking at what I get right now and what I got 10 minutes ago, what I got 20 minutes ago, what I got 30 minutes ago. Yeah, so the input gate is really just like multiplying kind of like element-wise zeros and ones with the current state. The forget gate is modeling the same thing, which is different parameters. Zeros and ones multiplied the state that we carry over from the previous step. And the forget gate is doing the same thing again, but on the output, right? So once you merge once you create the current hidden state from the current input and previous hidden state, you again do some kind of output gate where you regulate how much of the hidden state you computed right now is going to be outputted at this moment. Yeah, otherwise, you know, I mean, there is some element plus multiplication, there are some sigmoids, there are some hyperbolic tangents. It's just a different mesh. Now, there are many more variants of these, right? There are some LSTMs with peepholes where you look more at also like the CT, which is kind of like the memory state. So it also models on like how yeah, like you look more on those. The GRU gates, the GRU RNN cells, they, for example, I think they only have input and output gates, they don't have the forget one. So like, there are different ones that you can experiment with, and this is actually something that is really neat. You don't actually need to implement this from scratch because TensorFlow has it built in, and they actually also have built in quite a lot of other RNN cells that are being published. You know, like there is a new research, they implement the cell and then they put it, you know, they probably make a pull request. There's usually like a paper reference that like, okay, this cell was based on this research paper, and you can just use it. It also explains what are the arguments for it, which is really neat. Yeah, a really good resource that talks about quite in depth about both RNN and LSTMs and like sequence modeling in TensorFlow is the blog on wildml.com. I really encourage you to check it out if you haven't come across it, but I mean, I think it pops up as the first thing if you Google RNN, so I mean, there's not really a way if you can, you know, go past it. Cool. Now, okay, so how do we implement it in TensorFlow? And there's this unofficial quote from Google where they say, you know, there are always two ways to implement stuff with Google. There's one that's deprecated and doesn't work anymore, and there's one there that doesn't work yet. And it's also the case with TensorFlow a little bit. You find some TensorFlow tutorials that are like, you know, guaranteed to work, and they probably did a few months ago, but now you run them and you get a whole bunch of errors. You're like, okay, well, what do I do now? You look at the documentation and then, you know, you find all these other functions, but you can't find any examples for them because there are none, and like, you know, so what do you do? So this is the old way. This won't work anymore. This is how we implemented it because the TFL stuff, we actually did it in October. So some stuff has changed, but the main idea still stays, right? It like, you kind of, you know, depending on how your data structure is built right now, you know, you need to do some reshaping based. So basically, if you have like one row per timestamp, you need to get the input for the RNN just right, which is kind of going to be like a list of tensors for the last 8 or so inputs. So you kind of need to reshape it. You can either pre-process it, but then your data set is going to blow, or you can do it on the fly and it's going to be slow. So I mean, there is no good choice for this. Then you do kind of like LSTM cell. So this is how it's implemented. It's quite cool. It's both in Contrib, but it's also, I think, now in the main framework of TensorFlow, not just in Contrib. You can also do like a few RNN cells as well, because, you know, why not? And add some dropout on it, and then do the RNN that doesn't work anymore. That is now, I think, like the static RNN one. I think TensorFlow tried to implement a lot more of dynamic RNNs as well to kind of, you know, follow the torch path as well. But yeah, so yeah, they're doing improvements, and like those improvements are huge leaps forward. You don't always see them because it's under the hood, but like yeah, I think if you want to keep your code ready and working, I mean, it requires constant maintenance. So this was one way to do it in kind of like the rawest TensorFlow, and a few months ago. Oh yeah, that's the reason why you want to use stacked LSTMs. You just stack more layers instead of doing proper analysis, and it usually works better. Yeah, there is also another way. So there is this TF-Learn framework. So again, this was a few months back. I think it was around January or around that when it was written. I think TF-Learn is now kind of like also merging a bit more into the normal TensorFlow API in kind of like the, so you can just import learn from TensorFlow, and then yeah, there are all these layers and so on. So this is again not, I would implement it like this today, but I mean I think this should still work. It's a lot shorter. It's a lot kind of like neater. It's really just 5-6 lines. Today I would probably choose an implementation kind of like based on the newest things, which is basically you define an estimator class to which you pass a model function, and the model function is probably the best to use either the combination of raw TensorFlow code if you think you need it, or just the TF layers if that is something that can make your code neater. And that's what we do currently. Okey-doke. And then we also, so then we got our hands on a few GPUs, which was quite cool, and we decided, yeah, let's test this model on like quite a lot of data and see the performance increase. So we adjusted the model to do to be able to work on multiple GPUs. What it does is really just splits the batch across different GPUs. So that's the for loop in the middle. It splits the batch. You have basically a computational graph on each GPU. So the model is small enough to fit kind of like entire on a GPU. You compute basically for each quarter of that batch, you compute the gradient, you average them, and then you apply it. Yeah, it gave us some quite neat speed increases. I think these are those. So I think with only a CPU, which was I think kind of like a simple baseline, we were able to process like 8 kind of like those time elements in per second. You can see that with the 4 GPUs, we're playing with the batch size. The increases are 125 more. It was a massive increase. It was a pleasure to play with. Right, and now we're probably interested in the results and like what we got. So like we're trying all these LSTM approaches on time series, and we might be asking, is it any good? It was actually quite good. So the scale of data and the timeline that we had, it was kind of like a hackathon project in like 2 weeks. Didn't really allow us to kind of like train a full kind of model for the entire London. So we try to scope it down to make it more manageable in that time frame. We only chose the West corridor leading into London, and we only used 4 weeks instead of the 3 months of data that we had. But the problem still stayed. We used 40 minutes lookup in the past to predict 40 minutes ahead. Yeah, and so these were some of the graphs. Like then it's quite difficult to make sense of like, so what is a good prediction, because how do you actually predict? So what we did is we visualized the predicted values from the 40 past minutes and kind of like matched them and overlaid them with the real value that actually happened later. So this, I think, is visualization on the test set, which was held out during the training. And I mean, to me, that looks quite impressive that like this is one model, right? And each line shows a different sensor, and each column shows a different day. And yeah, of course, somewhere they don't match completely, but to me, it also shows kind of like a neat prediction that like, I would originally just expect like, yeah, what if the RNN just tries to predict the current state as the one in the 40 minutes. So what I'll have is the exact copy of the graph, but just with a 40-minute lag. And like that's exactly what we expected, and like we're kind of like afraid of like, yeah, well, if this happens, I mean, why do you train this massive LSTM if all you can do is just like, YT equals YT minus 40 or something like that? That would be really embarrassing. But yeah, I think it actually looks quite good, and we triple checked whether we didn't, you know, shift it way too much or something. But yeah, it looks quite good, and the predictions were, yeah, you can see them yourself. Yeah, so I think that was it from the machine learning side of things, and new stuff in TensorFlow are popping up all the time, and one of the new ones that we noticed is the TF transform, and that is actually just, this is kind of just like a taster of what it can do and maybe why it is worth having a look at it. It's basically, it helps you, so if you pre-process your data with Beam and you use these TF transform functions, you can then do the same pre-processing during inference. So because we create these bespoke models, it is very important for us to basically repeat the same pre-processing as we did, not just, you know, on like a whole of the training data and the test data, but also once the model is in production, you want to do the exact same linear transformations, maybe scaling, normalization, as you did with the training data on the new data points. And what this allows you to do is to define a beam transformation, like a beam graph, using TensorFlow functions and some special kind of like TensorFlow transform functions. Pre-process your whole large data set once, so you don't have to do it multiple times. However, it also allows you to look at the whole data set at a time. Now, then basically you can do stuff like, I don't know, normalize some features, right? And how else would you do it? If it wasn't for this, well, you would probably, yeah, you would scale it to 0 and 1 or like to -1, 1 range, but then that is some kind of a linear transformation, right? You need to subtract the mean and then divide by standard deviation. But those are parameters that you need to apply again on inference time. What TF transform allows you to do is save those as a graph and then just attach that to your inference graph that you serve with just TensorFlow. Now, when does it come useful? Again, I think there's a huge use case with the NLP, because, for example, if you have a huge data set, you need to do some vocabulary. You need to do a word mapping, so basically each word corresponds to one vector, so you can then have, you know, like some embeddings, for example, word to vec, which you're going to look up. But this kind of like word to int embedding, you need to make it once on your training set and then use it again during inference. And this allows you to do just that. You can also do stuff like TF-IDF and so on. So, I mean, we haven't played much with it just yet. We looked at it and we find it really exciting. So we really think this is the way forward, and yeah, do check it out. Okay, just to recap. So these are some of the tools that we used. It was a system that, yeah, could deliver these predictions real time. Now we can see the complexity that was, you know, you ingest the data, you ingest the new data, like new data coming in as a stream. You do online kind of like pre-processing with data flow. It's coming in stream. You do some online machine learning requests to, well, we used Google Cloud, so we use CloudML, but I mean, you can use any kind of API calls, and then we output the predictions again to PubSub. And BigQuery, yeah. So this was kind of our architecture. We use LSTM to do the predictions and Beam to do the transformations. Cool. That was it for me. Thank you very much for your attention. And I'm happy to take questions if you have any. Yeah. So
you didn't use anything from the geometry of the placement of the sensor again. You flattened everything and then learned the geometry from the database.
Exactly. So that was at least the assumption, like, yeah, this would be really neat if it worked. That you don't need to specify that like this intersection is more related to these than all the other ones. We thought about using some kind of geographic distance as a measure of kind of like give it as a precondition that like we know that this will affect it more, so to kind of like write it into the model. We didn't get to implementing that because it was kind of like out of the scope at the moment. But it's a great, I mean, that's the avenue I would go with. Yeah.
So you use the stacked LSTM. So what's this benefit over a single layer of LSTM?
I don't really know. It was really just the picture, you know, like the layers with layers. We just kind of.
An experiment to see if a single layer of LSTM and a stacked layer of stacked LSTM. So how do they
Right. So again, like, I mean, you saw the evaluation. It was mostly looking at graphs. We got some numbers, some, you know, like distances of like the regression problem that we were trying to predict, but those don't really tell you anything because you don't know the scale. So really, like, this wasn't like a fully proper, like a machine learning kind of like scientific experiment, like finding the best model. The graphs looked a little bit nicer. Okay. Thank you very much. Oh, anyone more? Great.
Yeah. So is TFL actually already applying your?
Oh, we wish. No, this was like a hackathon. We didn't make it into kind of like a project stage where we would actually apply it. We kind of did it internally. Then we had some talks with them, but it didn't really go anywhere. So yeah, no.
One day.
Maybe. Yeah. Thank you very much.